Okay, so we saw in the last video, simply we just need to switch the x's and y's around to create an inverse relationship. Now, if we were given two separate functions, so if we were just given an f of x function or a g of x function, we have a system that allows us to test whether the two functions would be inverse functions, and this is going to use the composite function relationship that we learned about in the last video. Excuse me, we're having pen problems again. So a composite function is when we substitute or embed one function into the other function. And so when we do this, if we were to create a situation where both composite functions equaled to x, so if we took the two original functions, f of x and g of x, and we made a composite function going both ways with them, and they both ended up in x, that basically means that the two functions would be proven to be inverse functions. So if we can prove that f of x actually has an inverse, then we can say that that inverse can be written as f of negative 1, f to negative 1 of x. So that negative 1 power, if you recall, represents an inverse. So we could write the inverse with that inverse notation just so that visually and from a naming standpoint we can see that is the inverse of x. So if we start with the original function of f of x and we do have an inverse, then we would name it f of negative 1 of x. So we're going to start here with two functions. And the directions, and this is important, say to verify. Okay? Now it didn't say to take the first one and switch the x's and the y's around. It said to verify that f of x and g of x are inverse functions of each other. And if they are inverse functions of each other, then that means that the two separate composite functions would both equal to x. And so that's what we simply need to do. We need to replace x with g of x, and you can see here in the f of x function we've replaced the x value in the f of x function with the g of x function, and we've created the composite function. Now in this first composite function we get a value equaling to x. Now this does not guarantee that they're inverses. Remember, both composite functions are going to have to equal to x to prove that they are inverses. So it is required for us to go the other direction. So you can see here simply that in place of f of x, we're going to put the function f of x in place of the x value and g of x, and so we create a separate composite function that also equals to x. So since they're both equal to x, that means that they're inverses of each other. So simply saying that if they're inverses of each other, g of x could also be written as f to the negative 1 of x, which is the inverse notation. So if we want to represent an inverse, we do so with the f of negative 1 notation. Okay? So in this last example, all we simply want you to do is to practice using composite functions to help prove or verify, as the directions state, that the inverses that they're inverses of each other. Now, directionally wise, we probably should or could write this as g of x until we absolutely prove that they're inverses of each other. But either way is fine. So you can you keep it as f of negative 1 of x as an inverse, and we're just going to prove that they're inverses. Or you can do it f of x and g of x separately if that makes it a little bit easier for you. So go ahead and pause the video at this point and work sample problem number 2. Okay, so on this particular one, and I'll keep it simple here, I'll do f of x and g of x composites. And so f of x was -3 times x plus 6. And I'm going to want to replace that x value with the entire g of x function, or the f of -1x. And so it's -1/3 x plus 2. Now, I'm going to need to distribute the -3. And so when I do this, -3 times -1/3 is simply going to give me a positive x. Then -3 times +2 is going to give me -6, and then of course I have the +6 on the back end of this. And you can see very simply that those are going to cancel each other out, which is exactly what I would like to see happen if I'm looking for inverses. And so you can see that this first composite function is equal to x, which is good. Now, it doesn't change the fact that we have to verify the other side of this. So now we're going to take the g of x function, and inside of that we're going to plug in the f of x function. So it's very important that you understand composite functions here from the previous lesson to be able to work these types of problems. So as we do this, again we distribute. -1/3 times -3 is going to give us a +1x. -1/3 times 6 is going to give us a -2, and then of course we bring down the +2, and we're simply left with x. And so our second composite function also equals to x. And so now that they're both composite functions equal to x, we can simply say that we've verified that they are inverses of each other. And so that's simply how you would work that problem. Now, if I wanted to do it with inverse notation, I could easily write this in this manner. I could say that this is, if g of x is the same thing of f of -1 of x, which is the inverse relationship, I could simply say that this is f of -1 of x. And so that's the same thing. So you may see it written in that form, and then of course if it's g on the outside, that's the same thing as f of -1. So those are two alternate ways to write this same composite function. So if you see this on a worksheet or in a textbook or something like that, but instead of using the g of x we use the inverse notation, don't let that throw you for a loop. It's still a composite function relationship. And that is the end of our inverse function lesson.